All right, today we're going to talk about condensed configurations. It's a shorter way of showing an electron configuration. Sometimes I will also call these noble gas configurations. So let's do this. Let's take a look at the periodic table, specifically let's look at barium. So barium has 56 protons and 56 electrons. So let's write the electron configuration for barium. Now follow along. I'm just going to go through the periodic table. Remember we talked about blocks, so let me walk you through it. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Let me say that again. Count the electrons, see if I got all 56. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2. Did I get all 56 electrons? I sure hope so. So what if I said there was a shorter way of writing that electron configuration? Would you be interested in learning about that? Oh, these are known as condensed, as the name implies, or noble gas configurations. Here's how it works. A noble gas or condensed configuration uses the symbol of the noble gas that precedes, that means comes before, the element for which you're doing the configuration. The noble gas symbol is placed in brackets, should say in your notes, followed by the configuration of the remaining electrons. So again, let's go back to barium. What is the noble gas that precedes or comes before barium? Remember, the noble gases are all the way on the right side of the periodic table. So that noble gas is xenon. Let's try that again. There we go. Xenon. So here's what we do. We're going to take the symbol for xenon and put it in brackets. So let me write this first. What does that mean? XE in brackets. Here's what it means. Listen carefully. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6. That's what that means. So you put all of that in this bracket. So then we continue. What comes after 5p6? Now we're down here. Sixth row, 6s block. Second position over. Xenon 6s2. It's as simple as that. All right, let me give you some others to practice. Let's write the condensed configuration for lithium. I'll walk you through it. So take the noble gas that precedes lithium, which in this case is helium. Helium ends with 1s2. So what comes after 1s2? Let's put this in brackets. So that means 1s2. And then all we have left is 2s1. All right, here's one for you to try. Go ahead and write the condensed configuration for sodium. Pause the video, please, so you have time to do this. So the noble gas that comes before sodium is neon. Again, when we put any in brackets, that means 1s2, 2s2, 2p6. So we're continuing from 2p6. So go to the third row, 3s1. All right, go ahead and write the condensed configuration for potassium. Pause the video. So the noble gas that comes before potassium is argon. And then we continue with 4s1. What do you notice here? So we see that lithium, sodium, and potassium, which by the way are in the same vertical column on the periodic table, they end kind of the same way. We'll talk more about that in just a little bit. Let me give you another one to try. Let's do, I don't know, titanium. Write the condensed configuration for titanium. So for titanium, it's argon in brackets, 4s2, 3d2. All right, pause the video, do the condensed configuration for selenium. So here's what we get for selenium. So it's a much shorter way of writing an electron configuration. All right, don't confuse condensed configurations with valence shell configurations. Sometimes they're similar, sometimes they are not. Says that the electrons in the outermost principal level, or the electrons in the highest energy level, or the electrons that are the furthest from the nucleus, are known as valence electrons. These electrons are really important. These are the ones that are primarily responsible for bonding in atoms. So when we say an atom loses electrons to form, say, a cation, the electrons it loses are valence electrons. Or when we say an atom gains electrons to form an anion, the electrons it gains go into the valence shell, or the highest energy level. For valence shell configurations, we usually only write these for elements in which the last electron placed on them is in an S or P sublevel. So we're talking about the S block elements and the P block elements. We typically don't write valence configurations for elements in the D block, or that middle of the periodic table. So let's take a look at some examples. We already saw the condensed configuration for lithium, sodium, and potassium. By the way, a condensed configuration does show all of the electrons. It's just we can write the noble gas in brackets, and that represents the 2 or 10 or 18 electrons before what we actually write. All right, so let's do a valence shell configuration. First thing is this. Very important. The row or period that an element is in on the periodic table represents its highest occupied energy level, or valence shell. For example, find lithium. What row on the periodic table is lithium in? So we see that lithium is in the second row, or second period on the periodic table, which means its highest occupied energy level is the second energy level. So we're going to just start there. Start at the second energy level. Again, we always start with the S, so start all the way on the left. Again, this time we're only showing the electrons in the highest energy level. We start with 2S, and lithium is the first position in the S block, so 2S1. Take a look and find sodium. Sodium is in the third period on the periodic table, or third row, which means its valence electrons are in the third energy level. So let's just show the electrons in the valence shell for the sodium. We get 3S1. And then potassium, I think we see a pattern here, 4S1. What do you think the valence configuration for rubidium is? That's right, it would be 5S1. What do you think the valence configuration for cesium is? 6S1. So something we'll talk about later on is that elements in the same vertical column have the same number of valence electrons. We see that here. All those elements in the first vertical column have one valence electron. Let's try a couple more examples. Go ahead and pause the video and write the valence configurations for magnesium, calcium, and strontium. So hopefully you got these. Let's try some more. I'm going to walk you through a couple more here. So let's write the valence configuration for nitrogen. So let's find nitrogen on the periodic table. Right here. What energy level are nitrogen's valence electrons in? So we see that nitrogen is in the second row, or second period on the periodic table, which means its valence electrons are in the second energy level. Now be careful, unlike the other examples we've done so far, in the valence shell of nitrogen, there are two different sublevels. We have an S sublevel and we have a P sublevel. So we need to account for all of the electrons in that second energy level. So be careful with this one. So again, we start all the way to the left with 2S2. And then we have to account for the electrons that are in the 2p sublevel. And there happens to be 3 electrons in the 2p sublevel. All right, let me give you an example to work on. Go ahead and write the valence configuration for sulfur. Go ahead and pause the video. So we see that sulfur has 6 valence electrons, has 6 electrons in its highest energy level. Go ahead and give this one a try. Pause the video, write the valence configuration for bromine, and tell me how many valence electrons bromine has. Hopefully you got this. Some of you may have put 5s2, 4d10, 5p5. Let me show you something. Remember, the valence electrons are the ones in the highest energy level, so we're looking for the biggest coefficient in the electron configuration. How about those 10d electrons? Are they in the valence shell? Are they in the highest energy level? No, they're in the fourth energy level. That's what that number means. So those electrons are not valence electrons. So be careful. A valence configuration is not the same as a condensed configuration without the noble gas in brackets. It's sometimes very, very different, like in this case of bromine. That concludes this lesson. Thanks for watching.